topic that we are going to cover today is the activation functions. Now, uh, what they are, we know, we have studied a little bit. We know that for each neuron in the neural network, there are two sort of phases. We called it the magic box with resistors and so forth. We take the input, multiply them by the weights, and then we get what we call the Z, which is the result of the affine transformation. Then we pass that result, that becomes a final input, we pass that result into a distortion function, an activation function that does some form of nonlinear transformation on that input signal. And when you do that, the result is an activated output. That's the vocabulary or the language that people use. So while we have been doing it, and we have been using that, I've been talking about the tanh and the ReLU, and in the code, we have been using these. You have seen that in practice. Today, we'll give this session to understanding activation functions in depth. It turns out that these activation functions, there is more to it than just thinking that they are a distortion function and we can use what we want. There's a long history to it. People are continuously researching better and better activation functions. And you can actually get a considerable, sometimes surprising performance gains in your model simply by using a better activation function. And the reasons are varied. Some of the reasons are that in complex network, certain activation functions lead to certain pathological conditions, let's say dead neurons or vanishing gradients or exploding gradients or shifts and so forth. So there are quite a set of problems that you can have in a very deep, complex neural networks. So you have to play with these activation functions and see where which ones is more appropriate. And sometimes to find which one is more appropriate, you can narrow your list of the activation functions that you'll try by theory, just thinking through it, reasoning through it, and you know from experience that this is what you should use. At other times, it is not so obvious. The fact that even today new activation functions are continuously emerging just shows how important they are and how active an area of research they continue to be. So I will use a sort of a historical progression to talk about these distortion functions, as I have called them in the past, or the activation functions. Right? And today, let me see if I can stand and talk instead of sitting and writing. If I do so, are you guys able to, am I still visible?
Yeah.
Yes, sir.
Perfect. Still perfect. Okay.
You should stand more, sir. That's good.
Yes, I'd like to do that. And it's an experiment today. Let's see. So with that, let us go back and review a couple of basic things that we have done. The reason I kept this today as an extra session is so that we don't cut upon the next 3 weeks. The next 3 weeks are crucial. 1 week is on computer vision, another week is on natural language processing, and another week is on graphical neural networks and possibly anomalies in fraud detection and things like that. So when we talk of activation functions, let me recap the notation that we used. We said that there is such a thing as I will call it a neuron, right? A neuron, or we also call it a node, right? And this node has inputs coming in. You have inputs x1, x2, and xn coming in, right? And associated with each of these inputs, you have a resistor that is the sort of the physical intuition I gave that manifests itself as the weight, W1, W2, W3, right? And then there is a dummy input, which is sort of a weight 1. We call it either a bias in the literature, or we call it W0, right? And so what this produces is a summation. This sums up all the products. So it produces something that I will call the Z, which is produced in the first half of the neuron. This is equal to W0 plus W1x1, W plus Wn xn. Right? It is just a linear product. And this product, people write it in a slightly different way quite often. They will write in a more abbreviated or mathematical or vector notation. They will say that, suppose you consider the weight vector to be this, 1, W1, W2, 3, and Wn. And then if you think of likewise the x vector, do you notice that we have augmented it with a 1 in front of it just to take care of the bias? And oh, sorry, this is W0. And this is 1, x1, x2, to xn. When you do this, then you say that the dot product of these vectors, which we can represent as this thing, W comma X. You will see a notation like this, which explicitly says is W comma X. You will see a notation that says W dot X in the literature. And you will also see, so this is, I suppose, inner product. These two are thinking of it as an inner product. And an equivalent way in matrix notation is to think of it as a W cross X matrix multiplication. So what does transpose means? Instead of a column vector, if you were to make W transpose would be W0, W1, Wn. Like this. And so you realize that matrix multiplication is only possible if you take the transpose of W in this. And the end result of all of that is exactly the same when you do. So end result is Z is W transpose X, right? And that is our basic result, is equal to this W0 plus W1 x1 plus Wn xn. Right? So this is hopefully a review of what we have done so far. Right? Now, let's think of what it is doing. Your input feature space, let's say that you have 3 dimensions. So suppose this is your R to the N, right? This is your input feature space. Isn't it? And what Z is doing is, it is using a mapping from Rn to R, because Z is a number. When you do a dot product, you end up with a scalar, right? And so you are going from the X vector to the Z, which is just a number, using the weights, using this transform, using the dot product. This is saying the same thing in a more sort of a mathematical or succinct notation. But all these different ways that I express this fact, they are all equivalent. So that's a summary of where we are. But that is not all that a neuron does. After Z is computed, we also have one more stage to it. The second stage that we have is we apply a distortion function. This is usually called an activation function of Z, activation function of Z. So it is this function, this distortion function, that is the topic for today. We will give all our time to talking about the distortion, about this sort of activation function. Now, distortion function is a word that I use. People don't use that. They usually call it activation function, or a more common word that people use is is transfer, not more common, actually less common word, is transfer function. So I will mention those things right now. Activation function, activation function, transfer function. What do they do? They are mappings, essentially. They do something different. They take Z as input. So Z is what? It's just a number. And they output what? They just output a number. Are we together, guys? Output the activation, let me just call it A of Z, right? This is the activation of G, and that is also just a number. So the first thing you notice that this activation function is a univariate function, therefore. Is that evident? Is that evident, folks? So we conclude that the activation function is a univariate function. So you can just say the output, which I will say y, let me just call it the output. A is equal to some function of Z, isn't it? And Z being a function, and so it is a function of your weight and the inner product of the weight and the input. So this captures the relationship so far. So far, so good, guys. Are we all together so far?
Yes.
Recap. So this is a recap. And so today we'll focus on activation function. Now, the first thing we learn is what should it be? Right? If you just sit back and think, what should activation functions be like? So you can think of many answers. The non-answers would be the bad answers. So let's write this question down. What should an activation function look like? Let's ask this question. So one way to do that is by asking, what shouldn't it be like? So what are bad solutions? Bad solutions. And that will give us an intuition on what a good solution. Bad solutions could be, suppose you say that activation function A of Z is equal to 0. Means, what does it mean? The output is always 0. Would such an activation function be of any use?
No.
No.
Yeah, it generally wouldn't be. It represents, in other words, it stops the flow forward. So if this such a neuron was sitting there in any layer and inputs were coming in, and such a AZ is equal to 0 were true, what would come out guaranteed is 0? In other words, this neuron is effectively a dead neuron, isn't it? Right? In other words, it stops the flow forward, i.e., the neuron dies. Neuron dies. So that is easy to see. Well, and the same is true. What about this? Can we go and say AZ is just some constant? What about this? And reason through it, guys, you know, when I talk about activation function, I'm deliberately starting from first principles because I want you guys to develop the theory in your mind and reason through this. So tell me, is this any use?
No, it's almost the same.
It is the, yeah, why? Because this term, if all that this is doing is producing a constant, to the next neuron that it is going, there will be bias term, and you're just adding C to the bias term. It is as good as having 0 here and adding C to the bias term, isn't it, guys? So this would be about as useless, not very useful. Then comes another solution. What about a linear? So let's take this question. Suppose AZ is equal to Z always, i.e. for all values of Z belonging to the real number line. So from -infinity to +infinity, whatever input you give, it always produces the output as that. So this acts as a pass-through gate, isn't it? True.
Meaning that you don't have an activation function?
No, you do have an active. It doesn't distort it at all. It just lets it go through. It's just a pass-through. Right?
Okay.
It's sort of like an open gate, isn't it? Whatever comes in goes through. So imagine that you have a gate open, and whatever gets in gets out, right? So that's what a linear activation function is. And you could say, and its variant is, and its variant could be C times Z. So up to a multiplicative factor, it just scales it. What about this now? So let's reason through that. It's quite interesting and to see whether this could lead to some interesting possibilities. So let's take two neurons. I'll take two neurons. Let's say that this neuron is there. And I'll create a neural network like this. And let us say that you take a one-dimensional input. So let's keep our life simple and reason with this. So suppose this is here. This is weight 1. And this is the weight in layer 1. Since I use a superscript for layers, W1, and this is the weight in layer 2. Yeah? And let us say that this has some bias, a bias of the layer 1 and a bias of the layer 2, right? Or W0, if you want. They're equivalent, right? Let's see what happens. This activation function, it will produce Z1, Z of the first layer. Let's say of the first layer, what would it be? It would be B1 plus X times W1. Does this look, let me write it in the more conventional notation. W1 times X is the same thing. Would you agree that this would be true?
Sir, yes.
Go ahead. So the output here, what would be the output? It would be the output of this activation, this Z1. Just get transferred and come out as Z1, isn't it? Z1, because it's your, or up to a multiplicative factor. Let's take this situation. Z1 just comes out as is. So Z1 becomes the input to the second thing. So what is Z2? Let us figure out what is Z2. Z2 is a bias 2 plus W, weight of the second layer times
Z1,
isn't it? And now let's see what this leads to, and this is equal to B2 plus W2 B1 plus W1X, isn't it? And then once again, if the activation of this is the same, if that is what comes out here, Z2 comes out, this is the response. So if you think of what comes out of the gate of the two layers, the two neurons, what comes out is this. But if you think about this, I can rewrite this as W2 here plus B1 W2 plus W1 W2X. Right? So this becomes your Z2 with just a little bit of algebra. Do you see that, guys?
Yes, sir.
But now comes an interesting thought. You could have instead of that, what if you had done this? You had just created a single neuron, right? Where the weight here was, so this is the weight, right? And this is the bias. Let me put primes here to indicate that we are talking of another, and this is the Z prime. So suppose you had a neuron whose B prime is equal to B2 plus B1 W2. It just so happens that you set it to be this, and your weight W prime here to be for the input is equal to just W1 W2. So now think about it. What is the output here? Z prime is B prime plus W prime X, right? And if you try to break it up into the original terms, it becomes the original equation, isn't it? It becomes B2 plus B1 W2 plus W1 W2X. Do you see that, right? These two are equivalent. These two are equivalent statements. So what are we saying? That the yellow neural network, the two-layered network, in this very simplified network in which we are taking only one node per layer and just a single variable input, that situation can be summarized by saying we don't need any of the hidden layers. It is just, you can have an output right here, a linear regression output, Z prime coming out with our identity, like where your activation function is AZ is equal to Z, right, as the activation function. See, guys, is this little bit of algebra convincing? All we have said is that if you only do linear, like if you just do identity transformation or identity activation, you will get, there is no need. You can take two layers and they will act as a single neuron. And now you can generalize 3 layers, 4 layers, 5 layers, whatever number of layers, you can squash all of them into a single neuron. Is that looking convincing enough, guys?
Yes, sir.
Yes, sir.
Isn't it? So from that we draw a conclusion. Let us draw a conclusion. And by the way, if you do a multiplicative factor of C, all
If the blue one, the
yeah,
B prime, can you please repeat?
yeah. So is that something to me? Somebody saying something to me? Okay.
Yeah, Asif, can you please explain B prime once again?
Yeah.
The blue one.
Suppose your activation function is this. So now think about it. Suppose you have a two-layered neural network, and each layer has a single neuron. X goes in, output comes out. The output of the first layer goes into the second layer, and the output of the second layer comes out here. Work out the equation. What is Z2, the output? When you look at Z2, you'll realize that you can write it in terms of all these weights and biases, isn't it? Are we together? Right? Why? Because the input, if you really look at it, the output of the first layer, let me just write it here, output of the first layer. And what is this? This is the output of the second layer. Right? Would you agree?
Yes, sir.
Yes.
It's simple, no? But the thing is, you could, when you plug in Z1 here, you can expand it out. And when you expand it out, you notice something very interesting. There is grouping in the data. And so you can actually write an equivalent single neuron, just a single neuron that will do the job. So long as its weights and biases are like this, they're defined like this. If you define the weights and biases of the next, just a single neuron like this, it will do the same job as your two-layered neural network is doing.
Yes, sir.
Is that clear now?
Sir, it looks like a equation for straight line, I can see that. So the slope will be weights only, and the y-intercept is the b2 plus b1 and the,
Yes,
yes,
exactly.
right, exactly that.
You can think of it as this is your bias term. That's why it is b prime, and this is your slope, right?
Got it, sir.
The weight part, or the y prime, w that, right? You can write it as it. So what do we learn from that? What we learn is, and by the way, I did it with c is equal to 1, the proportionality constant equal to 1. I'll leave it as an exercise for you to convince yourself that if you bring in that multiplying factor, nothing changes, the arguments remain the same. You're just adding c to the mix. What we learn is that a neural network with many hidden layers but with linear activation is, what is it? What can we say about it? It is equivalent length to a single neuron with linear activation, isn't it? Now, when you write z is equal to, like, when you write z is equal to some bias term plus some weight times x, when you write it like this, what are you doing? This is what equation? If I were to just change the wordings a little bit, is this reminiscent of y hat is equal to, remember in the earlier course we did beta 1x, right? Or beta dot x from your ML 100, 200. Do you remember this? Or in one dimension, this is beta naught plus beta 1x. Do you remember this, guys?
Yes,
Yes,
sir.
sir.
Recall from
Linear regression.
right. So what is this? This is just nothing but linear regression. This is the equation for linear regression, isn't it? For linear relationship. In one dimension, it's a line. In higher dimensions, it's a hyperplane. So what you're saying, therefore, is that we can only capture linear relationships, isn't it? And that is a crucial fact. Means we don't need so many layers. It is useless. We can just start with a single neuron and it will get the job done. It's practically no different from that. All this complexity is not needed. So now we came to two of these things that don't seem to serve the purpose very well. Let's try something else. What about this? Let me try another thing. What about, and so far, guys, before I move ahead, this is a very important thing. Typically what happens is, if you take a course in machine learning in any one of the universities at the graduate school level or, or in the upper division level, like fourth year, third year engineering students, you're often asked to prove this in your homework. Typically you leave this, you go prove this. Right? So because this idea is important, right? So now what about this? Imagine an activation function that goes like this. So it is undefined in this region. Right? So it is a discontinuous function. I should write it better. Discontinuous function. So what will happen now, guys? Will this serve our purpose? Suppose this is Z, this is A of Z. What
Which
would
seems to violate all the manifold requirements, even though it's the activation function.
Very good, that it would. And very practically, what if the value of Z falls in this region? Z value based on inputs and weights evaluates to the, let me call this region, to the missing region.
Bermuda Triangle.
So it would just fail, isn't it? You wouldn't be able to use it. The whole thing would stop. So we can't use, so we learn a lesson. It has to be defined. So from that we learn a lesson. The activation function should be defined everywhere in the domain R, which is in other words from minus infinity to plus infinity. So for what it means is for every value of x in real number, that is minus infinity to plus infinity, along the real number line, we need a value. We must be able to evaluate this function, isn't it? Something like evaluate the activation of, actually let me use Z because I'm using Z everywhere. AZ must be able to evaluate AZ. So that's a lesson to learn from that. And so we learned something. And now logically, let's proceed a little bit further. We now stipulate that function better be defined everywhere, but we haven't really fully dealt with discontinuity. So suppose I have a function that is like this along the Z axis. This is Z. And let's say that you have a function that is like this. And then this is at this point, some point, doesn't matter where, it goes like this. What about this? We have a function defined everywhere, but it has a discontinuity.
So it's not differentiable.
Right. But what will happen is we will not be able to backpropagate. Backpropagation requires derivatives. So we end up with a problem zone, non-differentiable point, non-differentiability. And also it leads to very unstable behavior, right? There's also unstable around Z. Let me just call it Z tilde, unstable around Z tilde. Means very small perturbations, very small changes of values. If you're on this side of the boundary, the value is this. If you're this side of the boundary, the value just suddenly shoots up, isn't it? That is usually not a good idea because you want small changes to have small effects, not dramatically different effects. So that also doesn't seem to be. So the lesson here is, we learned the next lesson. Lesson is activation functions must be continuous everywhere. So the reason is non-differentiability, cannot take gradient derivative. Gradient, let me just say gradient for backprop. Now, so activation functions must be continuous. And along with it, let's also throw in the caveat that what about differentiability? You need differentiability also, isn't it? Differentiate. What is differentiability? A big mouthful of a word. What does it mean? Must have a derivative everywhere except perhaps a couple of points. So you allow it to have missing a derivative sometimes, and you'll see where, except perhaps at z is equal to 0. And why this is there and you can get away with this, we'll come to that. Right? It turns out that it doesn't bother you because when you back propagate, whichever way you look at it, you multiply the derivative. There's derivative there of the loss function. You're also bringing in, well, some other things, the weights and so forth. So the only way z is 0 is if the input is 0. Right? If the input itself is 0, well, then it doesn't matter, right? You are in trouble. So so there are reasons to say that a couple of points are okay. This is differentiability, though, is useful. There are other qualities that you want. First thing you realize is that you want non-linearity. What I call distortion property. Your activation function should take the input, the real number line, and distort it, right? Otherwise, you won't be able to capture nonlinear decision boundaries. Am I clear? So we saw that, right? It can, otherwise it becomes linear regression. That is another lesson we learned. In other words, to capture non-linear relationships, mappings, if you want to be more formal, of Rn feature space to either R regression or Rn to, you know, what was this? Categorical classification. So this is literally a nonlinear relationship, isn't it? You would say y hat is some nonlinear function of x, where x vector belongs to the input feature space, which is n-dimensional. Okay? And here you would, so your function should represent, to be able to capture a nonlinear embedding manifold, okay, hypersurface. You do need distortion, a neural network with distorting output, you know, activations, nonlinear activations. The same is true in classification. You can have nonlinear decision boundaries. Decision boundaries. So nonlinear decision boundaries cannot be created, as we just saw, by a linear activation functions. Right? So nonlinear decision boundaries or nonlinear embedding manifolds. Manifolds, embedded manifolds. Embedded, actually, embedded manifolds. Manifolds. Right? You cannot do that if you're, it's a hypersurface. With curvature, with bends, and so on and so forth. So nonlinearity is an important criteria that you want to have. There is another criteria that you want, which I'll sort of mention. It is a good to have, it's important. But if you don't have it, you can get away with it. So let me use another color. Boundedness. We didn't talk about boundedness. Bounded. If it is not bounded, so in other words, if the value for some input z, for some z, if az is very large, is very, very large, why is that a problem? Because suppose this one is producing the layer L is producing, this layer L is producing this activation Z, it is the input to the next L+1 layer, isn't it? And so if this input is very large, what will be the Z, what will be the Z L+1B will become very large, right? So then you have a problem. The problem is you either normalize it, so you need to, so it can risk some activation functions, the activation of the next layer, some next layer activations with saturation, right? It's just a bad idea to have such a large outputs. And so, but usually batch normalization solves it. Remember, we talked about it. At each level, the outputs that come out, batch normalization, like pulling the values back in, usually solves it. So today, boundedness is important, but if you don't have it, we don't worry about it too much. Batch normalization usually takes care of it. Right? So important, but not necessary. Important, but not necessary. So these are some properties that you expect the activation function to have. And the last one is actually a property that I'll just mention to you. Suppose you have an activation function that, suppose, let me use this different color to talk about this topic. Which color should I use? Let's try green. We haven't used green. Zero-centered. Zero-centered. What are we talking about here? The zero-centeredness. See, suppose, now this is too thin. Suppose AZ is always greater than 0, right? Or greater than or equal to 0 for all Z. So then what happens? Your values will tend to keep getting shifted, you know, to the positive, right? Things or outputs keep getting shifted, keep getting limited to the R plus, the positive values, right? And so you lose half the number line for the next layer, right? You have squashed it to only the positive values. So that is a bit of a concern, because unless you normalize it, right? So you have to be careful. You have to be careful to batch normalize before the next layer activation. It's just a thing. So what it means is that to be zero-centered is to have both positive and negative valued outputs. Okay. So in general, it's a good to have. Good to have. Now, as we make progress, and I'll take you through the various activation functions, one of the things you'll realize is that to fulfill all the criteria is sometimes neither desirable nor possible. But there are some that you can't violate. For example, continuity is not something you can play with, right? It must be there. The second is that differentiability must be there, except for maybe a point or two. Non-linearity must be there. So the ones that are there in these three are not negotiable. The boundedness and the zero-centeredness, well, If you have it, it gives you benefits. If you don't have it, then you have to have an adaptation mechanism, a compensation mechanism to take care of it. Right? So that is it. So in other words, let me summarize what we learned. Activation functions in neural networks, they cannot be a constant valued or zero valued. That wouldn't be useful. They cannot be the identity transformation pass-through. They cannot be even just a linear multiplication of pass-through. They simply cannot be linear. Otherwise, you won't get the full richness of a machine learning model. Those functions should be differentiable and they should be continuous. They should be bounded. So those are absolutely necessary conditions. Then come certain properties which, if you have, lead to benefits. One of them is boundedness. In other words, the values don't just explode or so forth. And the other is zero-centeredness. Means you have both negative and positive values. So as we work our way through the different activation functions, keep these 5 properties in your mind, and we will see how well they play with these 5 properties.
Sir, I have a question.
All right. Asif, I have a question. So, is there a problem if if we don't if the boundedness, if we allow our gradients to explode? Is it because of computational complexity, or is it just is there really something beyond the computational power that's the
We'll
problem?
come to that. Why do we have exploding and vanishing gradients? It's slightly different from boundedness, Patrick. See, a function can be large, value can be large, but at that large value, the gradient, the derivative can still be very small, isn't it? So in other words, let's say your altitude, you're next to Mount Everest. So suppose your function is height function. You're close to Mount Everest, right? And so your value is very high. But what about the slope? As you know, the slope is finite. No? Otherwise, you won't be able to climb Mount Everest. Am I making sense?
All right, I see. I get it.
So there is implicitly one more property, which I call monotonicity. Right?
Sir, I have a question on zero-centered. That you were saying that batch normalization will solve the problem if it is not zero-centered,
Because
like only in one half.
if the output is positive, it will pull it back in. What does a normalization do? It will spread it typically between -3 and +3. So it will zero-center it. That's what normalization.
I see. Okay.
So if the activation function is not zero-centered, you have to add something to it to make it so, right? Make the next layer inputs to be zero-centered.
Follow-up question there, Asif, for zero-centeredness. So are there instances where where it's okay to allow our model for that layer, particular layer, to have just positive outputs?
It is perfectly okay. And this was one of the realizations. We'll talk about it. It was actually some of the things we'll learn when we discuss the different activation functions. Not all of them are zero-centered. So then what do? Fortunately, things like batch normalization comes to our rescue. Because it zero-centers the input before it is fed into the output, before it becomes the input to the next layer. Right?
I understand. But let's say you want your output. Let's say it's for some reason that layer is discovering borders. So let's say you actually want it to be all instead of penalized, you just want them to always either reward it. Would it be beneficial to just allow your outputs to remain positive?
Yes, there are situations where you do want that. So it's not case by, and this is one of the things you'll see in a few moments, that as we go along, we will encounter many activation functions. There's a rich library of those. In fact, PyTorch has implemented a pretty rich library of activation functions. Maybe I should, I have added it to the course page. Maybe I can give you a sense of the richness of it right now. It is worth looking at it just to see why, it's a question like, why would people worry about creating so many activation functions in a industrial strength library like PyTorch? Yeah? Is because when you experiment with different activation functions, you get a lot of benefits. So if you go to the course webpage, you will actually, I put the activation function topic pretty up so that you can immediately spot it.
So as a good practice, it's better to be zero-centered, but just pick a good activation function rather than allow the output to.
Reality is complex these days, right? We realize that we would like a zero-centered, but the cheapest activation functions that get the job done are not zero-centered, right? So in fact, ReLU is not zero-centered. Yet it gets the job done. But you can't have, I mean, you just need to have compensating mechanisms like a batch normalization. So really is something I'll introduce almost immediately in a few moments. It is the topic for today, but I wanted to show you something, guys. This is the activation function this is the documentation. I don't know, the fonts are very small here.
Wait, Asif, before you go on, monotonicity is a necessary attribute, right?
Yes, I was going to come to that. So hold on. That is the last one I'll talk about. So nonlinear activation function. Do you see how many there are? And most of these you haven't heard the name of. If you look at typical code on the internet that people have posted at tutorials, etc., they will always use either ReLU or Sigmoid or TANH or Softmax. Right? This is about it, but there's a pretty rich library, and there's a reason why. In fact, just changing and knowing these activation functions and knowing when you should change one for the other, sometimes, it's a free increase in performance. And in a world where even a few points of performance gain, accuracy gain, matters a great deal in production, in real life, isn't it nice that we can try out the different activation functions and sometimes hit the jackpot, get just that little bit of extra performance to take us over the victory line, sort of, in some sense, right? So you can see a lot of these activation functions are there built into PyTorch for a reason. They all have a purpose, and we should be more familiar with all of them. So in the textbook, in your lab textbook and these things, the richness of it is not discussed. I feel that this topic needs more depth, has more depth than we do justice to in the introductory textbooks. So today, that is why we are holding this session. So with that preface, we have been through almost to 1 hour. I would like to do one more thing. What did I just do? I did something. Okay. The last point that I was coming to is a property that of activation function that we want, right? And that Dennis referred to. See, we don't want an activation function that behaves like this. Why do we not do that? See, for neural networks, it doesn't serve a purpose because we want to generally have a situation. The word activation inherently has the idea built in that bigger Z, as Z increases, A of Z will increase, or at least not decrease. So at every point, if as you move along the Z-axis, it increases, what does it have to be? Therefore, we expect AZ to be increasing always, or at least not decreasing. This property is in mathematically, we call it the monotonicity. Monotonicity. The word monotonicity comes obviously from music, right? In a constant pitch, sort of one direction. It doesn't change direction. Now, I'm not a music expert, so I can't speak with expertise what really monotonicity is in music, but I suppose the word monotone in the common sense has something to do with it. Any musicians here who would like to enlighten us on the word monotonicity in music? No. So guys, this is, I would like to take a small break of 5-10 minutes for you to digest this thing. Think about it. See, I'm building the concept of activation of functions from the ground up, from logic, from first principles. And it is best to understand it from first principles, slowly, right? Let's go back to fundamentals. I'll review it again. So this is a big neuron. The yellow thing is a big neuron. It has two phases to it, two parts. Remember, we talked about it as a magic box, which is made up of rheostats that produces the output Z, right? And that it sums over so it's basically Z is the inner product of the weights with respect to the input, right? So Z is W dot X, inner product. And that's another way of saying that you basically take all the inputs and you take them in different amounts, right? In common sense way. So those are the two ways of formulating the same concept, mathematically and in common sense. But then you take the Z and you apply an activation function to it. That activation function needs to have some properties. If you reason through what properties it should have, you would agree that it would not be a good idea for the activation function to be a constant, right? 0 or possibly 0, because that is as good as a dead neuron, right? A constant value is a dead neuron, right? But this is not a very good situation if you end up with. So we don't want that. The next thing is, what if you make it linear? The simplest linear is just a transfer. AZ is equal to Z. A different one would be AZ is equal to C times Z. So it turns out that when you do that and you have many layers in your neural network, then the entire network is equivalent to actually just one neuron, right? You don't need all this complexity. So that is an important observation. Just one neuron will do the job. You don't need so many of these. Right? So that is another lesson to learn. And when you do that, when you have a single neuron, as you remember, the single neuron with a pass-through activation, linear activation, is nothing but linear regression. Right? It is the equation of linear regression. And linear regression, as we remember for our ML 100 and 200, it just captures a hyperplane. Right? It does not capture the complexities or the non-linearities of a generalized embedded manifold, right? Or hypersurface that captures the relationship between feature space and the target space. It does not, right? Cannot possibly. It will always be a flat hyperplane. So therefore, our linear activations are not something that will serve our purpose. And therefore, we need nonlinear activation functions. So that is one lesson to learn. What else do we need? It's a discontinuity, of course, and differentiability are important. You cannot have activation functions that are either not having any value. This is worse than that. This region, has no value here in this undefined regions. You cannot have that this function is undefined in some part of the real number line. It must be defined everywhere, and it must not have discontinuities because you lose differentiability, right? That's one thing. So it must truly be continuous. And then differentiability, it better have derivatives everywhere. The one special point where you can sort of get away by not having derivatives is that Z is equal to 0, but otherwise you should have derivatives. So that is it. And then non-linearity. Non-linearity is at the heart of it. You want to capture non-linear relationships, you better have non-linearity in your distortions in your activation function. Then only a conspiracy of many neurons will together capture the features of a nonlinear embedded manifold, a relationship. That is it. Then comes two properties which are good to have. Boundedness, it just says that the value should not just keep on getting large, because then it puts the next layer into trouble, because with very high activations, you can, well, there's a set of things that can happen. If you're using a sigmoid or something like that in the next layer, it will just saturate or something. This is not a big problem these days because batch normalization fixes it, solves the problem. So we don't put too much emphasis on boundedness. But nonetheless, if an activation function comes with boundedness built in, it's a good to have. It's a good property. Right? Zero-centeredness means it should have both positive and negative values. If it only produces positive values, again, you're shifting, everything to the positive part of the real number line. Right, and the input to the next layer will have no negative values. Well, the cure for that, of course, is batch normalization will cure that. Yeah. It will input. And then also the weights, because if the weights, some of the weights are negative, it can put the weights there. But otherwise, without some balancing technique, compensatory technique, what will happen is all your weights will drift one way. The other thing is simple. The other thing that is not negotiable is obviously the basic inherent notion of a activation function in the neural network is they are monotonically increasing. They're always increasing or remaining flat, but they are certainly never decreasing with Z. Right, so that is, and that mathematicians call the property of monotonicity. Monotonicity means it has only one behavior, either increasing or decreasing. In this particular case, increasing monotonically is what we want. Right? So those are the properties that we expect neural networks to have. Now what we will do, let's take a quick break. I will very quickly review the backpropagation, and then we'll go through each of the activation functions. I would like to cover at least four or five, and then show what properties do they have, what are their plus and minus, when you should and shouldn't use them, and so forth.
Sir, there is a function, a swish, which actually...
We'll cover it today.
Yeah, that over there, yeah, so it will decrease, and I think that's a much better representation of biological function,
We'll do swish today.
Thank you, sir.
Yes, yeah, all right. So,
sir, one question quickly. Asif sir, say if there is linear relationship in the data, if it captures the decision boundary, then why cannot we use the neural network? I mean,
you can. The only problem will be that the only times it will work is when your data truly has linear relationships.
That's right, correct.
Other situations, it won't work. But see, a priori, before you have played with the data, modeled the data, you don't know whether the relationship is linear or not, isn't it?
Correct, right.
The reason. You don't want to presume that it is linear and continue with that.
Okay, so I have a question about monotonicity. So you mentioned, monotonicity is either increasing or decreasing. But
Yeah.
your above statement, it says, we expect A of Z to be increasing always, or at least not decreasing. So
Yeah, so monotonicity is more general. In the case of neural networks, we want one specific monotonicity. We want monotonic increase.
then how does decreasing come into picture?
There is no decreasing, right? You don't. You tend. I mean, see the typical as we go through it. So you don't decrease the. You don't want that as Z increases, delta Z is positive. You would like to have delta A to be positive, right? That's all it means. It means that the slope should preferably stay positive. But we'll have more to say about that as we continue. See, all of these properties, to what extent we need to adhere to them and to what extent we can compromise on them or not have them. That is the topic of interest in the. So guys, I'll start by saying that certain conditions, just to summarize, you can't compromise on. and certain you can. So you must have a continuity, and that is not compromisable, right? That is a given. Must be well defined. Differentiability, otherwise you can't differentiability, except at 1 or 2 points, except at 0, etc. You must have differentiability, right? But the conditions that can be broken, they are boundedness, B, that they are this monotonic. It turns out that a little bit of violation of monotonicity is okay. Can be violated. People used to think it cannot be violated, but recently we learned actually that a lot of new activation functions break monotonicity, but they do it in a very strategic way, very sort of a careful way. And then the zero-centeredness is another thing that can be violated, can be broken. So now what I will do, guys, is I'll try to recap backpropagation in a few simple statements and see whether we are able to do that from yesterday. So backpropagation, as I said, is a topic that will take a while to sink in, and we'll do it over and over again. I'll keep using different topics as an opportunity to sort of review backpropagation. So let's take backpropagation in a very, very simplified situation, because that will serve for us. So suppose you have a situation like this. Here is W1, here is W2. And we'll take a single dimension input and imagine a chain of neurons. So it's a very simplified neural network in which each layer is a single neuron. And if you get this one right, you get the more generalized multi-node per layer also. So suppose this is W. So this is the layer 1, layer 2, layer L-1. This is the layer. And let me use the word L to be the last layer. Right? It is going in. So what happens is W1, W2, WL-1, WL is going in. And then the last layer. And then what happens is that the activation of the last layer is the output, is the y hat, right? So now you can compute the loss function out of this. You realize, right? So you can compute the loss function. Example, mean squared error, MSE, you would write loss is equal to y hat minus y squared, right? And 1 over n and so forth. Let me just write it here. And this is the summation, 1 over n. Am I making myself clear, guys? Is this looking familiar?
Yeah.
1 over n. This is your loss MSE. Loss is like this. So what do we do? So actually, you know what? This is cluttering up my image. So let me, this picture that I want to explain, let me write it somewhere else. Loss function. Example of loss function would be, let me write it here. MSE loss 1 over n summation y hat minus y I square. This is the MSE loss. So now what do you do? If you have a loss function L, then the thing that you can do is you can compute the gradient of the loss with respect to the activation, with respect to y hat, for example here, activation of the last layer. If you can do that, the idea is that this will help you compute the gradient of the loss with respect to A L-1. And that will help you compute the gradient of the loss with respect to the activation in the, you can keep going one, and now I'll put dot, dot, dot here. Let's say with respect to 2, and that will help you compute gradient with respect to the first. Right? So it keeps going on. It keeps moving backwards. You can keep computing the gradient layer by layer, right? And now, why is that relevant? It is relevant because at each level, if you ask, what is, see, you want to make this step, the delta step, the gradient descent step is W next for any particular W next, and I'm deliberately dropping all the indices just to keep the notation simple, because it means any one of the weights in this entire picture. Its value is the previous value minus the learning rate times dl, the loss function, with respect to W. So this, I hope we remember as the gradient descent step. Descent step. The real learning step. Isn't it? Now it turns out, so this is what matters. What we care about is this. Now let's look at this guy. It turns out that this thing you can express in terms of the activation of that particular layer. W. If you know the gradient of the loss with respect to the activation, you can compute the gradient, you can compute this. At each layer you can compute this. Because the activation helps you decide this or figure this out. And we'll see this with very concrete example. You will actually see that backpropagation or the derivatives, they're not as mysterious or as complicated. They're very trivial actually, but you have to see it with some specific activation function to see that. And so you can compute at each level accordingly. So this process is the, when you compute the activations at each of these levels, A1, A2 coming out, A3, AL minus 1 coming out, L minus 1, and AL coming out here. This is the forward pass. There is a forward pass of and a backward pass. Forward pass is just computing the activations, and backward pass is just computing the gradients. So let me. So now you might say, do you want me to show you how these things work? Just as a recap. First of all, let us recap. How can we compute if we know gradient of the loss with respect to some activation, then gradient of the loss with respect to W, weight, because that's what you'll plug into the gradient descent step, is quite simply equal to this. You just have to reason like this. If I change the gradient a little bit, what changes? Small change in gradient will change the activation function, right, of that layer, because activation function is, sorry, not activation function, the Z. Z is ZL is gradient of L, weight, weight, inner product of weight and the inputs. Whatever the input is. What is the input? L minus 1. It is this, which in the one-dimensional case, it just becomes WL, A L minus 1. Right? So this is ZL. So if I change W, ZL will change, and so I can write it. But if you change ZL a little bit, you realize that activation will change, because activation is a function of ZL, right? It is some function of ZL. So this will change the activation of the layer L. And if you change the activation a little bit, it will change the loss function a little bit. And so what have you done? You have shown that there is, and I'll write it succinctly here, the loss with respect to WL is equal to this simple product, WL, this multiplied by activation of this with respect to ZL, multiplied by the loss function of the loss with gradient with respect to the activation. So now we related these two things. Right? All you need to do is multiply the gradient with respect to activation with two multiplicative factors, and you get the gradient with respect to W now. Now the other thing is that how does the back propagation itself work? How do you compute the gradient of the loss with respect to in the previous layer based on the value in the layer ahead of it? Right? So let's do that. That is the other bit of thing we want to do. So let's again write it. We want this. How can we express the gradient of the loss with respect to the activation in one layer before in terms of gradient of the loss with respect to activation in the layer ahead of it. So let's work through the mathematics here. Let's do that. So once again, we reason from here and move to this. We say, let's see, you know what? Let's look at that. If I change the activation in the previous layer a little bit, what happens is that, let's think through this. AL minus 1 is feeding into the next neuron, which has a weight WL, and it will therefore affect the ZL, and then the output is the activation with respect to this layer will get affected, right? So let us see how we can work this out. Think of it this way. I change this, so let's put it here. A small change of this, AL minus 1, will change what? Would you agree that it will change Z? Right? Because that is the input to this layer, this neuron. So, so therefore, a small change in this will change Z. So let us say that. So this will lead to a small change in the Z of the next layer. A small change of the activation in the previous layer will lead to a small change of the Z. Now what will Z change lead to? It will lead to the AL, change of AL, the activation. This small change will cause this activation to change, right? DAL. And a small change in activation will, of course, lead to a small change of the loss itself. And so we achieved what we wanted to do. We related this thing in terms of this thing. Do you see that if I have the value of the gradient with respect to the layer L, I can find the value of the gradient with respect to the layer L minus 1. Do you see this, guys?
Yes.
And that is it. That is all back propagation is. What it means is that, but you know, you have to start. You just have to say, but I must know the gradient of the loss with respect to the last activation function. And the good news is usually we know that, and we'll see this with a few examples. That is easy. And so you can find the gradient with respect to the previous layer and the previous and the previous and so forth. And you're looking at back propagation, right? These are the two just essential steps. You just back propagated the gradient, back propped the gradient. And that is all it is, guys. That's all back propagation is. Then it's a recursive thing. You keep on going back and back and back. Right? So now, what has that to do? Notice that everywhere, this A keeps coming up. The activation function is at the heart of back propagation. And the shape of the activation function determines how the back propagation will work. So I'll take an example to illustrate this. We will take the example of, let's say, regression. Let's say that your last layer has activation, linear activation, you know, AZ is equal to Z or something like that. Or maybe you're solving a linear regression problem. Suppose your loss we will take is the easiest loss to imagine because we learn regression first, right? So guys, is it okay if I just sort of, sometimes I'll forget this 1 minus n factor because it's just a multiplicative factor, right? If you can reduce this, it will automatically reduce it by a scale value. So you might see that I keep dropping the 1 over n. So this is the loss, the regression loss, sum squared error loss, or the MSE loss, etc. And it might have some regularization terms. I'm not taking those away, they're still there. But for simplicity, assume they don't exist. It will make your realization simple. So now let's look at some, historically, how these functions evolved. So a family of activation function. Historically, one could argue that the first one that we knew about, so let me change the color here a little bit. The first activation function, as far as I know, and I might be wrong, is this. Suppose you have the x-axis here, the xy axis. So z-axis, and this is the activation, AZ. The simplest one is, and this sort of mimics the biological system, the activation of a neuron and so forth. And the shape of this is, what color should I use? Let me use this and use a thicker line. So the shape of this is a stretched out S. Do you notice that it looks like a stretched out S, isn't it? So this, and its lower asymptote, this is a y is equal to, so here, of course, this goes in this direction. What is the minimum value that it can achieve? Minimum of AZ is, can you look at this picture and tell what is the minima, guys?
Minus infinity.
A, the activation. Y-axis, look at the y-axis. What's the
0.
value it achieves?
0, sir.
0.
And what is the maximum that it achieves?
1.
1.
Is 1. So, and observe, so this particular activation function is the famous sigmoidal. People often use the word in machine learning, in deep learning, they use the word sigmoid all the time. But more precisely, I suppose statisticians would call it the logistic sigmoid. Because to them, sigmoid is a whole family of S-shaped functions. But in deep learning, and this is the terminology you have to be careful with, deep learning people say that S-shaped, this shaped activations are sigmoidal. Observe the AL at the end. And they will call the logistic simply as the sigmoid. They won't use the word logistic sigmoid. They will just call it sigmoid, right? And we represent sigmoid typically with a sigma. See, you know, this is the Greek symbol. Sigma. Little sigma. So they write it as that, and the mathematical expression for this is sigmoid function. So suppose sigmoid of z is equal to 1 plus e to the minus z, right? Another way that you can write it, and those of you who did ML100 with me must be very familiar with it. If you think of sigmoid as a probability, you know, if it goes between 0 and 1, you can think of it as a probability, isn't it? So sigmoid z over 1 minus sigmoid z, that is called log odds, is equal to z. Right? This is there are two ways of writing it, one in terms of exponentials and one in terms of logs. So this term, the left-hand side terms, people call log odds. You know, and you know, these days election season is there. Most people talk in terms of odds. What are the odds that this guy will win a Senate seat or win the presidential election or that and so forth. So odds are numbers. You'll say 100 to 1, right? Or 10 to 1 or so on and so forth. Odds for and against and so forth. So the log of odds is z. Log as in a natural log. In mathematics, typically when we mean machine learning, when we mean log, we typically mean natural logs. Though in computer science, traditionally, when you mean log, you mean log to the power, to the base 2. Okay? But here, natural log. So you can write it like that. Now, this function has that quality that, so think about it. Let's observe this function a little bit. This function, and I'll just study the sigmoid a little bit in depth for you. This function, when z tends to minus infinity, what happens? Sigmoid of minus infinity is equal to 1 plus e to the minus infinity. So what is e to the minus infinity? Is 1 plus e to the infinity. And so what does it do to the denominator? It becomes infinity. And so sigmoid will tend to 1 over infinity is
Very small.
0.
0. Likewise, sigmoid of plus infinity is what? Let's figure it out.
Infinity.
Minus infinity. So e to the minus infinity is what? 0, isn't it? Which is the same as 1 plus 1 over e to the infinity. So this term cancels out and this becomes 1. So you realize that this function, which is why it seems to have the two saturation points, right? These are called asymptotes, lower asymptote. And the upper asymptote. Upper. This term asymptote comes from calculus, but if it helps you, just think of it as saturation points. Right? So asymptotes are saturation points. Saturation points. It saturates to 0 and 1 at the two extremes. Right? That is a rough way of thinking about it mathematically. So this is it. And now comes the interesting thing. If you go and look at it, if your activation function AZ, whenever we do computations, we need two things. We need the activation function, but we also seem to need the derivative of the activation function. Do we go back and notice that all over the place, we seem to have this term sitting there. Do you see this? Right? This term. The slope of the activation function with respect to z. So in other words, we do need the derivative of the activation function. Do you see that, guys? Lurking in all this backprop computation is the derivative of the activation function. Is that clear? I mean, I hope that is evident here, right? In this formulae, that sitting there, lurking in there, is the derivative of the activation function everywhere. Make sense?
Yes, sir.
Yes. So what it means is, it is not enough to know the activation. We need to know its derivative. So let's try to figure out the derivative of this function. When you have the log activation, this is something. Let's go back and do that derivation. You could take the derivative here, or you could take the derivative here. Let's take the log part because it's a little bit easier, and you'll see why. So you can write log sigma z over 1 minus sigma z is equal to z. Right? So this can be written as log sigma z minus log 1 minus sigma z. So those of you who remember the log a over b, just as an aside, basic of log is, if you have forgotten, a over b is log a minus log b. Just as a refresher back from your middle school days. This is it. Right? So I broke it up. And now one more fact. Log of x, derivative ddx of log of x is 1 over x. Are we together? So from that perspective, if I apply the log here to this, what I will get is 1 over sigma x, sigma z, sorry, right? D sigma. So this is it, d sigma z, dz minus 1 over 1 minus sigma z. And now the derivative of 1 minus sigma z is the same as minus d sigma z dz. Right? And that would be on the left hand side, and on the right hand side, what would be the derivative of dz with respect to dz? 1. Right? And so here, this is a little bit of calculus, by the way. If you don't get it, it doesn't matter. I'm just giving it for those of you who are interested. If you just take it out and dz, dz, 1 over sigma z, and then there's a plus sign here, plus 1 over 1 minus sigma z is equal to 1. And so let's solve this term. And by the way, this is a sort of thing, if you remember, you used to be very good at some point. In the denominator, it would be sigma z, 1 minus sigma z. And what would be the numerator? 1 minus sigma z plus sigma z. Right? And this whole thing multiplied by d sigma z dz. And this thing is equal to 1. Oh, lovely. Things are beginning to now sing a little bit, because this term cancels out, and we have this result, d sigma z dz times 1 over sigma z, 1 minus sigma z, is equal to 1, right? And therefore, you just computed the derivative of the sigmoid function. Sigmoid activation function is nothing but, you can write it in terms of the sigmoid itself, isn't it? So now going back to the, or if I just say AZ is sigma z, in this particular case, you can say that going back to our notation was the derivative of d a. And then, by the way, I'll abuse the notation. Between my partial derivative and my full derivative, you'll see me that I tend to mostly use the partial as a symbol, even though I should be using the full derivative here, but okay, just bear with me. 1 minus a for a is equal to sigma, right? Active sigmoid. And this is a profound result. It's very, very good result. Do you notice that something lovely happened? You don't have to, during computation, during backpropagation, you actually can get rid of the derivative. You don't have to compute the derivative at all. Derivative is this. It is just a multiplication. It is a multiplication of the activation with 1 minus the activation itself. So stop here and just ponder over it for a moment, guys. We have no idea how to compute derivative, isn't it? We know how to multiply. We can write some code that can multiply. And now, lo and behold, in our computation, when we are doing the backprop, it turns out that at least one of the derivative is, well, too easy. You can just replace it with this. And if you use a sigmoid activation. Isn't that lovely? Right? Is that simple?
Yes.
Yeah. And now comes another part. Let's go back and inspect. Maybe some other parts also we don't need to worry about derivatives and doing fancy numerical computations. Or maybe we can get away with a cheat. So let's go back and look at it. Oh, look at this part. What about this part? Right? These derivative of z with respect to the activation of the previous layer. So let us go back to that and see what it means. Z of the next layer is nothing but activation. In our simple, one chain, activation of the previous layer times the weight of this layer, isn't it? So suppose you have this layer. A from the previous layer is the input. Weight is WL, and activation AL comes out. Are we together? And where did ZL come? ZL is the activation here. Now, what is Z with respect to derivative of Z with respect to A? So let's go back and see what we are trying to compute. You notice that you're trying to compute this Z with respect to the activation of the previous layer, right? So we go back and look at this equation now, and I'm just restating what we are trying to find, Z layer with respect to A, L minus 1, right? This was the other term, this term. Now, do you notice that if this is true, it is nothing but weight. Weight. Do you see that, guys? Right? And so now the whole thing is beginning to sink, because it turns out that there's another piece of the derivative that simply doesn't need to be computed. We, of course, know the weights, isn't it? This is just the weight. Is just weight. And in the broad sense, when we have many variables and many nodes per layer, it is just weights. So this too is easy. And now let's go back and see, is this entire thing beginning to sing now? And is back propagation much easier than than it looked at first glance? So let's go back to this expression, and I will scroll back and remind you. Let's go back to this expression, the full expression. Look at this full expression. This, it turns out, we can do without calculus, without doing a numerical computation of gradients, right? It follows. It's just a weight. This also we got away. But what about this guy? Right? So if somehow this also, we didn't have to do some fancy numerical computation to find gradients, life would be lovely, isn't it, guys? Because then it would just be a multiplication of terms, finding the gradient. Do you guys agree with that?
Yes, sir.
Right? So now this is where, and that's the magic with backprop. Actually, when you do it with real activation functions and real loss functions, it becomes very simple actually. So let us take a loss function, that is activation of the last layer, that is your y hat, minus y. And can I just drop the subscript of the data point and so forth, just for simplicity? This is your loss, right? I'm assuming that there is a summation and all of those things. Do you agree, guys? This is a summation of, okay, maybe I should bring the subscripts back. Activation with respect to some input. Are we together, guys? So now look at this. For the last layer, can I compute this?
Yes.
Right? So what is the derivative of ddx of x squared? It is 2x, isn't it? So bring that idea here. What is it? It is 2 times activation, nothing but summed over I of ai. Do you notice that, guys? This is true, that the derivative is just this, just from analytical calculus. Do you agree, guys? Do you see this?
Yes.
And so the last layer gradient of the loss, I can write, I don't need to actually do any numerical computation. This is a straightforward, A minus A layer activation minus the actual target values, isn't it? It's the residuals, just the sum of residuals. So this is very easy. And so what it means is, let's go back now and say that at least for the last layer, the layer before the last layer, L minus 1 layer, this particular part, this thing, I'll just copy it over at the bottom. DL. So let's look at this. If I know, I already know, so known for last layer. So what about the activation for the layer before that? We said that this is small change in activation in the layer before that will cause a small change in Z of the last layer. Small change of Z in the last layer will cause a small change of activation of the last layer. The small change of activation of the last layer will lead to the small change of the loss of the last layer. So these were the 3 factors. And we just computed all 3. Right? So what was this? This just turned out to be 2 times, well, your summation, A of the last layer, I minus yi, the actual value, right? So this is what this turned out to be, right? What this turned out to be was A, like for sigmoid,
1 minus
A of the last layer, 1 minus A last layer. And what did this turn out to be? This just turned out to be
W.
If you take the derivative of this with respect to this, this is just the weight W, right? Of the last layer. And so now, do you see that there are no derivatives actually being done? You just computed the gradient without actually doing any numerical computation. Just look at this result. Do you see that, guys?
Yes.
Right? It's easy. And so therefore, can you compute delta L, delta A, L minus 2? Right? You realize that once again you can do it simply by just going one step back. And once again, you'll have the weight of the L minus 1 layer, the activation of the L minus 1 layer. And you already know, you just calculated the activation of the layer L minus 1. So L minus 2 can be found. And so you can keep moving back and keep computing the gradient. And once you have this activation, you know that you can, from this, you can compute the loss function with respect to any loss function. If you know this, at any layer, you therefore can know of this. Why? We already did that. Loss function with respect to the weight of a layer is small change in the weight will lead to a small change in the activation, a small change in the activation, a small change in the Z. A small change in the Z will lead to a small change in the activation of the layer. And small change in the activation will lead to a small change in the loss in the layer, right? So this was there. Now let's ponder over this. Once again, do you realize, guys, this is what? This part is nothing but this is just the input of the layer. What is the input to this layer? It is A L minus 1. Isn't it, guys? What is ZL? A L minus 1 times the weight of the last layer, right? And so when you take this, you'll get this term. When you take the activation, this again becomes your A1 minus A. And you just computed this activation with respect to that. So what happens is that all your gradients, therefore, you compute without actually doing numerical computation in the derivative sense. Right? And that is the magic. That's why backpropagation is feasible and cheap. If you were doing a lot of numerical computations, it would be horrendous. Right? Because if you remember your numerical computation from college days, a derivative takes time. It's an expensive computation. But it turns out that you get the derivative without actually doing the derivative. Right? And that's the magic. That's why it backpropagates. So this was true for the sigmoid function. So I'll use the same kind of a term. Now, sigmoid function, let's see which properties does it have. The good properties, is it continuous? It is.
Yes.
Is it differentiable? Differentiable is very simple. Whenever you hear the word differentiable, ask yourself, is it everywhere smooth?
Yes.
Smooth. Yes, right? It is. Now, is it monotonically increasing? Yes, right? Is it bounded? Yes, because saturation points are 0, 1. Right? Values are bounded in the output is bounded to this 0, 1 interval, isn't it?
Right.
So it is bounded. So now things are beginning to look pretty good here. Now comes the, is it zero-centered? Does it produce both negative and positive values?
Yes.
No.
Look at this, sigmoid of Z. This is Z. Does it produce negative values ever?
No.
No. So this is a violation. It does not have this property. Right? Now there was one more property. Is it nonlinear? Does
Yes.
it have nonlinearity?
Yes, sir.
It does have. So it seems to have gotten many things right, isn't it? And so it was actually the original sigmoid function, the activation function. When I talked about the universal approximative theorem, I believe the mathematician's name is Chevenko. He proved it. The original paper of Chevenko is in terms of the sigmoid functions, sigmoidal functions. And in particular, he took the sigmoid to prove it. So it works. Then the sigmoid has, you ask this question that, see, can I remove this deficiency of being zero-centered? What can I do to remove it? And it turns out that there is a close cousin of sigmoid function. It is called the tanh. Should I use a different color? Might as well. Huh? Let me go over to blue. There's another function, tanh. The tanh is interesting. So this is, I'm just like taking you through the historical evolution of these ideas. And so guys, do you notice that what is tanh z? Tanh z, does it have upper, is it a bounded function?
Yes, sir.
And what are the bounds? Upper and lower bounds?
-1, 1.
-1 to 1. Right? It is bounded. Is it continuous?
Yes, sir.
Yes, continuous. Is it smooth? Is it differentiable?
Yes.
Sir.
It is differentiable. Is it monotonically increasing?
Yes, sir.
Yes.
It seems to have hit, it seems to be hitting just about all of your points. Is it zero-centered?
Yes, sir.
It has both positive and negative values. So which is a big deal. A sigmoid wasn't. And then, is it nonlinear?
Yes, sir.
It is nonlinear too. So this is actually a very, very popular activation function if you in the sigmoidal family, right? A very popular, I would say the most popular in the sigmoidal family. Sigmoidal is this shape family, stretch test family. Stretch test family. So this is good. And so I want to deal with more sigmoidals. There are more. So for example, there is the error function sigmoidal, Gaussian sigmoidal, and so forth. There are more complicated things you can do, but we'll limit ourselves to sigmoid. Remember, sigmoid and sigmoidal are different. Sigmoid is just the logistic, tanh and the tanh. So let's talk about tanh. What does it look like? Tanh is e to the z minus e to the minus z, e to the z plus e to the minus z. See, you notice that this looks surprisingly similar to the sigmoidal, the ordinary sigmoid, the logistic function. Where is my logistic function gone? Backprop, no. Yes, look at this yellow thing here. Do you notice 1 plus e to the minus z? Does it look somewhat similar to this, guys? Pretty similar. So you ask this question, is there a relationship between tanh z and sigmoid z? This is a question worth asking, isn't it?
Right.
Turns out that there is actually. I'll let you confirm it. So I'm speaking from memory. So if I get it partially wrong, it's your job to correct me. Later on, go verify this and you can correct me later on if I got this. But just observing the relationship and inferring a little bit, you can convince yourself that this is true. Right? So what tanh is in some sense, it is twice, it's sort of an amplified version of the sigmoid, the sigmoid function. Right? And in general, when you do machine learning, I would always recommend that use tanh. Don't use the sigmoid. If you look at the textbooks, the two examples they give you is the sigmoid and the ReLU. So you think your choice is between sigmoid and ReLU. No, a sigmoid, in my view, should rarely ever be used. A TANH in almost all situations is superior to sigmoid because it converges much faster. It has a bigger range of variability. It goes from -1 to 1. It is not, it is zero-centered. And at the end of the day, it does have quite an effect on convergence. You can run it if you go to the, you know, the TensorFlow playground, guys? Do you want me to show you that? Why don't you do that to see that in real life? Let's go here to Tensor Playground. So here's the thing, guys. Do you see this activation function? Sigmoid is there, TANH is there, ReLU is there. Linear is just a AZ is equal to Z. Let it go. So what happens when I take sigmoid, and let me take a complicated thing here. I'll just leave these layers in place. And is this enough for it to convert? I'll take sigmoid and I'll run it and see how slowly it losses. You see the color change here? See how slowly it changes color. Actually, we need extra layers here. So let me do this. And let me add a few more downs because I know that they're needed. So let's try it again. Look at the loss function. See, the loss is 0.499. And we are using sigmoid. What are you seeing, guys? The learning is very, very slow, right?
Yeah.
If at all, it's just flattened out. Not going, doesn't seem to be going anywhere. You can increase the number of nodes and try it again. Still, you'll notice that the loss is not improving dramatically. Now, what I'll do is I'll replace it with something much cheaper. ReLU, I haven't explained ReLU to you. I'll do that in a moment. Let me put ReLU here and then start it. Do you notice that things are happening much faster? Look here. Right? Are you seeing that learning is taking place much, much faster and the loss is falling much faster? This is a complicated problem, and so it is still struggling. It will take more time for it to finish. Actually, let me do one thing. Let me take a little bit simpler example. Let's take this example. And I'll take ReLU and see how fast it works. Done, isn't it? On the other hand, if I do the same thing with sigmoid, see how it goes. You notice that it's going very, very slowly. It seems to hardly be making progress. And finally, it gravitated to it. Are you seeing it? And do you notice something very interesting? In the beginning, it wasn't learning much. And then suddenly it started learning, and then it came close to the solution. That's a problem with sigmoid, actually. And we'll talk about that. Now, the same thing if I do with TANH, it will be faster than the sigmoid, but slower than ReLU. You notice that TANH is much faster than sigmoid?
Yep.
I'll run it again and we'll see that. Let me read TANH. Look at TANH. There it is. It pretty much solved the problem. On the other hand, ReLU also immediately solves the problem. But the same thing if you try with sigmoid, very slow. And remember that it is learning slowly and suddenly it will start learning fast. You see the steep decrease in loss and then it flattens out when it comes to the answer. So that's a limitation of sigmoid activation function. You can use this actually to play with these major activation functions. So that's that. Now let's get back to where we are. This is it. Now TANH, now the question is, if you use AZ is equal to TANH, it is okay that this is the expression for it. But what is the derivative? What is AZ? What is this? This is equal to, and I'll state it, I'll let you verify it, and I'll at this moment state it without going through the derivation. This is actually equal to 1 minus A, 1 plus A, right? Which is 1 minus A square. Right? And by A, of course, let me be more formal. 1 minus AZ, 1 plus AZ, and that is the same as 1 minus AZ square. Are we together? So here we have a result. It turns out that the derivative of the tan H also can be written in terms of the activation itself, isn't it? And so here also we sort of dodged a bullet. We don't have to explicitly compute the derivatives. It is just given analytically by this expression. So tan H is a good property. Now, what is the problem with these two things? Sigmoidal functions. So people for the longest time used sigmoidal because they were trying to mimic the biological systems, and biological systems have a sigmoidal activation. So they thought they were on the right track and they were improving it. It took a long time actually to move from even sigmoid, the logistic one, to tan H. Really, it took a while. And then came an interesting breakthrough, and people began to, they were frustrated with some limitations of sigmoid and the sigmoidal functions. One of the limitations is, do you notice that for large values of Z, large positive or negative values of Z, what happens if Z is here? What does the gradient look like? What does Z look like?
0.
It is approximately 0, very small. So now, if you remember that learning is proportional to the gradient, what does it mean?
Almost no learning.
Yeah, so you will have very creeping, very slow learning. Isn't it? Not only slow learning, it will, in fact, keep on vanishing your gradients. Your gradients will, and ultimately what will happen is the layers that are early layers, so as you back propagate back, it turns out that most of your gradients will disappear. They'll become 0. And so your early layers won't learn anything. And that was supposed to be a pretty damning problem with neural network to such an extent that for many years, people just abandon neural networks. They say it's not a problem that can be solved, right? And maybe neural networks was a lovely path down, walk down the wrong path. So, and we'll talk about that in a little bit. So then people were in search of something better. And so after tan H, this was Hinton, and I believe it was Nair and Hinton, if I'm remembering it right. So correct me if one of you later on can check. It was Nair and Hinton who, did I write his name correctly? I think so. Hinton, who came up with a remarkable breakthrough. They said, well, what about an activation function that looks like this? Now I'll again change color. Let me use some other color. What would be a good color? Let's pick a color like light green. So what if I took ReLU? This is a little counterintuitive, which is why it took so long for us to discover it. Because you'll realize that it just puts a question mark on some of the properties that we want to have. So ReLU looks like this. 0. So in other words, the ReLU function is activation Z is equal to the max of either 0 or Z.
Right.
Okay. So another way to express it is equal to Z for Z greater than 0 is equal to 0 otherwise.
It's like all or none phenomenon, sir, right?
And that is where the word comes from. See, in electronics, when we use the word rectified, the word is rectified linear unit. So the linear part is very obvious, right? It is literally the definition. AZ is equal to Z in the positive half. In the positive Z values, this part of the right-hand side of the page or of this figure, of this chart, it is just linear. But in this part, it is 0. And the word, I suppose, I'm just guessing here, it comes from electronics because, see, suppose you have an AC current. How does an AC current look like? Looks like this, voltage over time. And you want to convert it, AC, to DC. This process is called rectification. You see that when you rectify AC, it becomes DC. DC current polarity never changes. So what will happen is it will become like this. Right? In between, it's just 0. And then you smooth it out. You do funny things. You'll put a solenoid or something like that, and you'll smooth it out. But I'm just going back to the basic electronics that you guys may remember, that the purpose of diode, for example, what does a diode do? It does that, right? It doesn't let current pass through in the negative direction. Does anybody remember these concepts?
Yes, they're coming back to me.
Yeah, yes, Kate, you did that. So yeah, that is it. That's where the word rectified comes from. So now let's look at the properties of rectified. It breaks. Is it continuous?
Yes, sir.
Yes. Is it differentiable?
Not.
Something at 0.
Except for the caveat, except at 0. Which you have to be careful. You have to argue that it doesn't harm you. Right? And it is a acceptable exception. Is it 0-centered?
Yes.
No, it is not. There are no negative values.
Yes.
Isn't it? Is it monotonically increasing? It is monotonic, all right. Increasing. That is there. And then is it nonlinear?
Yes.
No.
Now this throws people off because the word linear is there. They think that this straight line means this is a linear activation function. Remember what I told you. Linear activation functions can never capture nonlinear relationships, but it is actually nonlinear, right? Do you see this bend here? It would be linear if it was just like this. Everywhere it was like this. It is not like this. It is, there is a change of values here. It's non-linear. So in other words, you cannot just write it as y is equal to az is equal to b plus some weight wz. You cannot write it like that, or say v plus lambda slope. Linear relationship. It is not. You can never write it like this. You'll always have to write it in this expression with two values here. And so it is a nonlinear. So nonlinearity condition is fulfilled, right? Is it bounded? Oh, it turns out that, is it bounded? No, it goes up to infinity, isn't it?
Yes.
Right? So it violated two conditions. It was not zero-centered. It is not bounded. But there is something very nice about this thing, which is why Hinton argued for it. He noticed that, see, what is the derivative? What is AZ? What is the derivative of Z, of this activation function? It is equal to 1 or 0. Isn't it? Z greater than 0 and Z less than 0. Derivative is simple. So what does it mean? When you backpropagate, at least this part is just 1 or 0. So it means that it acts as a gate during back propagation, a gradient flow. People use the word in back propagation. As the gradient flows backwards, backwards, either it stops or lets it flow. It either stops or lets it flow back without doing anything, without modifying it, because the gradient is exactly 1. Multiplying anything with 1 remains the same thing, isn't it, guys? So that was a nice thing, except that this seems to have one problem. So it obviously improves upon the situation of this vanishing gradient or this slow learning. You notice that learning would be the same irrespective of what positive value you have. This is the rate of learning, and the same is the rate of learning with large values of Z. So it's a bit of a more democratic, sort of a more proportional situation. Whereas the logistics with the squashing function, they saturated the sigmoidals. So that is something to know. So now we learned about the ReLU. But the ReLU has a problem. Once again, because it is not zero-centered, generally you'll have to do batch normalization together with it, just to bring the values back in. Now,
But Asif, one quick question on the ReLU.
yeah.
So literally with the way the activation function works, if any of the coefficients are negative, it's going to drop those out of the model, right? It won't contribute anything to the model.
Yeah, if the Z that gets computed, the input to the activation is negative, basically, see, so let's think a little bit about it. What happens is that this node is peculiar. In the forward direction, if Z is 0, A is 0, right? So so the node dies. Let's think about it. And in the backward direction also, right? What happens is that if Z is, let's say that this is in particular, Z is negative. So, all the weights and inputs multiplied, if it becomes less than 0, it's terrible. Because not only is the activation 0, what happens to the gradient? dA, dZ is also 0, isn't it? For negative Z. So what happens is that this node is essentially a dead node for negative Z. So what happens is, as your neural network learns, if the forward direction inputs, it turns out that the previous layer sends it a negative input, that node pretty much dies, which is a big problem that you need to solve. So guys, when you look at ReLU, you realize why it was counterintuitive that you would use it. It is non-differentiable. It has this problem that some nodes can die, right? You have the problem of dead node. On the positive side, the gradient is, when it is not dead, the gradient is 1. So you don't have vanishing gradient problem in the way obvious sense. Right? So that is that. It turns out that ReLUs are extremely cheap to compute. So when Hinton started putting ReLU along with obviously suitable normalization, what he found is that the neural networks used to run almost a factor of 100 faster, or sometimes 1,000 faster, something like that, orders of magnitude faster than using any of the sigmoidals, using even tanh. Take a very complicated neural network and it will do that. Its weakness is, of course, the fact that you have a non-differentiability at the origin and that you can't have dead nodes. To solve that, people did all sorts of tricks, actually. What they did is do that. So they said leaky ReLU. The leaky ReLU says that let us have, here the slope is 1. But here the slope is alpha, very small value. So if the slope in the negative Z is less than 0, slope is this, and here slope is 1, then what happens? dA dz is equal to alpha for z less than 0. So what does this mean? It means that back propagation goes through. Goes through. That's why you use the word leaky. It still leaks through. It's small, but it leaks through because the slope is very small. But the back propagation will continue and the node won't die. It's a leaky ReLU, right? Then people were still uncomfortable with this. So then there are some exponential versions and so on and so forth that people dealt with. And we can talk a little bit about that. But then then came some activation functions that violated monotonicity itself. So there is the swish function, swish activation function. These are very, very recent. What it did is, it did something funny. It took the linear activation, right, and it multiplied it with linear activation is what? AZ is equal to Z. And it multiplied this, it took a product of this with sigmoidal or a sigmoidal activation function, right? So if you multiply these two, so it becomes, the activation function becomes x times sigmoidal, so Z actually, I should use the word Z, this is Z, this is Z. So now maybe I should change color, I'll go to white again. So it becomes 1, so Z times 1 minus e to the 1 plus e to the minus Z. Do you notice this, right? And so the couple of variations, the moment people discovered that this leads to a really good behavior, and this is fairly recent work, guys, and a lot of people are very excited about it. Now let me remember the exact shape of it. It goes something like this. It goes, I believe, like this.
That's correct, sir.
It goes something like this. So now you notice that, let's go back to it. Is it continuous?
Yes, sir.
Is it differentiable?
Yes.
Yes.
It is differentiable. Is it bounded?
Yes, sir.
Yes, it is even bounded. Is it zero centered? It is
No.
zero centered. Lovely. And but is it monotonic? Monotonic.
No,
It is not monotonic.
it is not zero centered also, right, sir?
No, they are negative. You have some negative values. Do you see those?
Yeah,
That
some.
negative values are there. Right? And by the way, it should have gone through 0. This line is not very accurate, but okay, just bear with me. Yeah? I'll post the actual shape of the swish and these functions on the slide. Is it non-linear?
Yes, sir.
Yes.
It's non-linear. And so what happens is that we have these functions and many more. If you go back and now look at PyTorch library, you will see that a lot of these activation functions are there. And they are variants of the other. For example, tanh, to make the computation faster, there is a hard tanh, right? Tanh. There is a hard sigmoid and so on and so forth. And these activation functions all are there for you to use. And we have observed that performance in many situations like image processing, etc., can be dramatically improved with these, because some of the pathologies that you have with a simple ReLU don't happen with the newer things that have come. Right? So when you're learning, when you read your book, like especially the book that you guys are using, you'll notice that it predominantly stays, if I'm right, with ReLU and tanh and linear and softmax. Is that correct, guys? Those of you who are reading through the book? It's been a while since I finished that book. You check it out. So it is. It probably mentions somewhere that there are more activation functions, but I want to emphasize that play around with activation functions. They actually lead to a lot of benefits, and this activation function that we are talking about, the one that I mentioned. Sorry, guys. Where is that one? Once again, I'll go to the page. So on the page, guys, I've given you the links to everything, huh? All of this. So you see the activation functions. Okay, hang on. Are you guys seeing my screen? I'll increase the font. Is it readable now?
Yeah.
So you see this activation function in PyTorch. You click there, go there. You will notice that, oh my goodness, see, look at the long list. Right? What I would suggest is, as time passes, become familiar with more. Make it an objective that every month you will learn, let's say 1 or 2 more. Right? CLU, for example, got a lot of attention. It again leads to a lot of improvement. And you notice that ReLU, after ReLU, there are a lot of variants of that and improvements on that. Even sigmoid has a lot of variants of that. Log sigmoid, right? And so on and so forth. TANH has hard TANH, right? Then Swish, a simplified version of Swish is the hard Swish, right? So there is no end to these activation functions. So take it as a homework. How about this, guys? Could you just use these functions and plot it out in a Jupyter notebook, each of them. See how they look. From -infinity to +infinity, when you plot them out, see how this activation functions look. It will be very easy. All you have to do is create a lot of numbers and then apply these activation functions. Are we together, guys? Right? This, and then also apply all of this. Now, softmax is something I would like to talk about separately. Today is gotten late. I guess we'll stop here. Softmax is in some sense, it is an activation function, but it's a very special activation function. We use it for multi-class classification. Right? So it has some variants to it and so forth. So with that, I guess I'll stop now.